Hello, everybody. Welcome to the next meeting of the club. So, what I'm going to do today is build off of the concepts that Christian introduced last week and maybe add a little bit of new stuff. Uh, there will be a little bit of maybe tricky math, but most of you should be able to follow along with some of it at least, I hope. Okay, so the first thing I'm going to talk about is the forces experienced in flight. Now, this can apply to anything like an airplane, rocket, even like a ball that's thrown into the air. Um, Many of these forces will still apply to all these objects. Now, these are the only four possible forces to create while something is flying. These are the only ones, and every single flying vehicle controls itself by manipulating these four forces. So you can see them up there: gravity, drag, lift, and thrust. Now I'll go into every single one of them in depth in the following section. Who's unmuted? Okay, they're muted now. All right. So gravity or weight. Now this is like a fundamental force that all matter experiences between each other. Now it's actually relatively weak, so there has to be a very, very large amount of matter for this to have any significant effect. Um, so it's ever present, like when anything's in flight, this is always gravity's always going to have an effect. It's the only one of the four forces that literally can't be turned off ever. Now, a common misconception is that there's since there's no feeling of weight while you're in orbit or something, or say on a escape trajectory, there's no gravity. This is simply not true. There's still going to be gravity. Um, it's just that your relative acceleration to your vehicle, for example, is going to be zero, right? You're not accelerating relative to the area around you, so that's why it feels like there's no weight. But it's always there, even like in outer space, like far away from anything. There's still going to be a little bit of gravity. Now, um, let's look at how it's calculated and the equations for it. So, if you're very close to sea level, anywhere on the Earth's like surface, really, this first equation can be used here. So Fg is equal to force. Fg is like means force of gravity is equal to mass times the gravitational field strength on their surface. Now this is on Earth. This is calculated to be 9 meters per second squared, and you just plug in your mass of anything you want to measure, and this will tell you the force. Now, in space, since this g is not going to be the same, the equation looks a little bit different. So, what it is this gravitational constant. Now, this is just a sort of a parameter or constant and it's always the same for every single thing in the universe. That's um, applied to these terms that actually change the meaning. Um, but this basically tells you how strong of a force gravity is based on the mass and the distance. Now, let's talk about the masses and distance. Um, so to get the force, it is directly proportional to mass. So if your mass doubles, of let's say one object stays the same. If your mass doubles, your force of gravity will double. If both of them double, your force of gravity will actually go up 4 times because you can see they're multiplied to each other. Um, Now, through experimentation, the people who created this equation also discovered that gravity is proportional to the inverse of distance. So basically, what this means, the further you get from a mass, the weaker the force of gravity becomes. And it's a squared term, so it's actually has quite a big effect. Okay, let's do an example problem. So let's say a satellite is in a 250-kilometer circular orbit around the world. Its mass is 200 kilograms. What is the force of gravity acting on it? And what is the acceleration that it experiences? It should say towards the center of the Earth. Um, this is the equation, remember? And here's the values that we plug in. So this is the G. This G is always going to be the same for every single gravity calculation that's ever done in the universe, in this universe. So in the top, you plug in your two terms. So this is taken directly from the question. This 200 kilograms. Uh, this is the mass of Earth. This is just a known quantity that's often memorized. And this is interesting at the bottom. So this section here, the 6,371,000 meters, is actually um, it's actually the Earth's radius, and that 250,000 meters is the distance of the orbit above it. So if you crunch all these numbers, you get this number here. So 1817.3 kilogram meters per second squared. Now this is what a Newton is. This is how you measure force. Now if you want to get acceleration, all you need to do is divide out the kilogram. So what you do, you take your original mass, right? Divide it out of this force, and you get your acceleration. So you can see that even in this high altitude, high altitude, like the acceleration is still very close to 9.8, which it is on Earth's surface. So still very powerful and a significant force that must be always considered. Let's talk about the second force, fundamental force in flight. So thrust. So um, thrust is essentially like the momentum you're imparting into exhaust gases that you're ejecting over time. So it's a reactionary force. So you put a force into stuff that you're throwing out the back of your rocket or jet engine or whatever, and that momentum will be imparted back into you. Now let's have a look at this first equation. So essentially what it's saying, so it's like the velocity of your stuff that you eject times the rate of mass that you eject is equal to the thrust. So another notation for this dm over dt is mass rate. It's essentially the derivative of mass with respect to time. Now let's have a look at this equation. So this essentially shows the true meaning of thrust. That applies to engines more than just this equation, because this equation doesn't consider a part of thrust. So this m dot over v2, so v2 is the velocity of gases at your nozzle exit, it's called momentum thrust, and it's the sort of, well, it's just a part of this thrust force equation. But this is also applicable to rockets. This is called pressure thrust. So many times on a rocket exhaust nozzle, you'll still have residual pressure, and pressure is basically force over area. So if you multiply the area out, you'll still get some force if your particles here are under higher pressure than your atmosphere. And this is a special case right here. This equation of when P3 is 0, so atmospheric pressure is 0. So this is basically what your thrust is while you're in space. So let's have a look at this example problem. So a rocket engine's exhaust moves at 1700 meters per second. So that's the V2 quantity from the previous slide. And the mass rate is 10 kilograms per second. The pressure at the end of the nozzle is 1500 kPa, so kilopascals, and its exit area is 0.1 meters, should be squared. What is the thrust at sea level? So this is the equation we're using. So we get our momentum thrust from this part. So flow rate, mass flow rate times speed. We get kilogram meters per second squared. These two multiply together, and that's just a Newton. Now here we take the difference in pressure. We multiply by the area. So yeah, Pascal is just a Newton per square meter. So these units also work out to newtons. And you can see we just add the two here together, the pressure thrust and the momentum thrust. This is actually very significant for momentum thrust, so I kind of made my area kind of big for these numbers. All right, now before moving on to lift and drag, I want to talk about some of the important like axis and reference lines that are used in relation to flying aircraft or any vehicle. Could be a rocket as well. You'll see this diagram come up in a later section of my presentation, but for now I'll just briefly explain. The most important one I want people to know is angle of attack. So what angle of attack is essentially you take this reference axis that goes directly from the front edge of the wing to the trailing edge of the wing. It's called the chord line or also plane of wing, and it's the angle between that and the direction you're flying. Now this is will be important for the lift section coming up. Um, and yeah, you can see there's some other lines that are important. So thrust. So thrust doesn't necessarily have to be in line with the direction of flying. And this is actually like for rockets when they're in space, drag and lift becomes zero. So that's the only way, and gravity you can't control. So that's thrust is the only way to control where you're going for a rocket, and it's a significant portion of your control in the atmosphere as well. We'll see this diagram later, and I'll explain the rest of the stuff on there in more detail. Okay, let's talk about lift. So lift is typically associated with like the wings of an aircraft, right? Sort of the force that they push up onto an airplane with. But every single object will make lift in the air. Even if like you drop like a knife edge through the air, it will make a very small amount of lift, but it still makes lift. Now, it is always perpendicular to flow direction. And I should also point out that it's always, while staying perpendicular to your flow direction, it's always pointed up as much as possible. But it doesn't always have to be necessarily straight up. So yeah, here's the equation. I'll go into the individual variables of it and I'll describe them a little bit more coming up. But it's important to note how mass is not a factor at all in this equation. So that is why airplanes are built to be light. And engineers spend so much time optimizing that. Okay, so one of the variables is rho or density of your working fluid. Working fluid essentially just means like what are you traveling through? So most of the time it's going to be obviously air, but you can have lift like in water as well. Like some ships they have like wings that stabilize the ship underwater, and they're actually super effective because like water is so dense, right? But usually we're thinking about air here. And the most significant factor is the altitude. Obviously, as you go higher and higher up, the air density drops off at an inverse exponential rate. So what ends up happening is you go from, I believe at sea level it's 1.2 kilograms per meter cube, and eventually just drops off to zero. But there are other factors too. So weather is a factor. If you think about like often they measure how severe storms are in terms of how low their pressure is. So storms they typically like create different currents and can manipulate the pressure in the air. So that is one factor. It's not as significant as altitude. Yeah, all of these like are super insignificant compared to altitude. Um, so temperature. So obviously the warmer something is, the less dense it becomes. So colder air is more dense. You can have more lift with all the other factors staying the same in cold air. Um, Moisture. So water vapor is actually less dense than just normal air. So it displaces it and moist air becomes less dense. It's kind of counterintuitive, I guess, because you think like, oh, how, like, because sometimes you feel when it's super moist, like the air is thick or something, but that's just the feeling. That's not what's actually reflected in reality. Okay, so flow velocity. This is actually the most like influential factor, honestly, because it is squared. If you remember the original equation, the it's u in the original equation. If I go back, this is the flow rate or relative wind. It's actually it's important to keep in mind. It's not like how fast you're going over the ground. It's how fast you're going through the air that matters for this. Now, uh, I mean, yeah, there's actually not too much else to say about it. It's pretty straightforward. But I just want to interesting point out something to note that in this picture, it's not actually a good condition for a wing to be. So you can see how um, all these lines here are super nice and straight, but here you have all these like swirls and eddies and vortices. They're basically all the same thing. Um, this is not good because essentially what ends up happening is you don't have this nice flow and lower pressure air over the top of the wing, and this significantly reduces your coefficient of lift, which we'll talk about later. So you don't want this happening. If your angle of attack gets too high, it's not good. Yeah, I'll talk about more about how lift is created later, and this may become more clear. I should maybe put it later. Okay, lift coefficient. So all other factors equal, this basically describes how good something is at creating lift with what it has. Yeah, that's probably the best way to put it. Like, this is what aerodynamicists spend like most of their time optimizing that work on this, that work on creating lift for airplanes and stuff. So it depends on the angle of attack. So typically a lift versus angle of attack graph will go up, and then there's some critical angle where the lift is maximum, and then it will just drop off because of stalls. Um, Now, yeah, lift, it depends on the airfoil shape. Yeah, if you have any like stall or flow separation or any issues with it. Yeah, in this diagram here, I put a few examples. So essentially, see how these more aggressive shapes that push the air downwards more have higher lift coefficients, but that always pretty much comes at the price of drag. So when people are designing airplanes, they have to think about this trade-off very carefully. Okay, and yeah, there's reference area as well. So this is the projected area perpendicular to the direction of motion. So for lift, yeah, this is kind of what they'll be referencing. So most of the time when engineers do this calculation, they'll take into account either like the whole plane or maybe just the wings and see how good it is at creating lift. Um, yeah, and this stays constant no matter what orientation. So essentially, even if you're flying upside down, you'll have like negative lift, but this reference area that you're projecting will stay the same. Okay, let's talk about Bernoulli's equation and Newton's third law and how they relate to how lift is generated. So there's like kind of two theories that both work in tandem and both do part of the explaining for why um, wings like this create lift. So I'll talk first about Newton's third law. So again, it's for every action, there's an equal and opposite reaction. So um, yeah, what that's saying is essentially when this air is coming and hitting the wing, it's getting deflected and pushed downwards, right, by the wing. Uh, and in order to deflect that, the air has to push back up into the wing, kind of like thrust as well. So that's how Newton's third law explains it. But there's also another part of it, and that's like Bernoulli's principle. And this is the equation of Bernoulli's principle. And essentially, what it's saying is it's a sort of a conservation of energy equation for fluids. So the pressure plus the um, kinetic energy plus the gravitational potential energy will always stay the same for a fluid. Now, for a wing, since you're basically changing your altitude very, very slightly, these H terms become insignificant, and you're only really looking at these two terms. Now, what wings do is they accelerate the air that goes above. So what that does, it decreases the pressure, right? And increases the pressure at the bottom of the wing. They slow it down here and increase it here. So what ends up happening is the pressure at the top drops, but the pressure from the bottom uh, increases. So you have this net pressure difference that pushes up on the area of the wing, right? So pressure is force divided by area, and you have an area, so boom, you have force. Okay, let's do a lift example problem. So an airflow around an airplane is 400 meters per second. The reference area is 100 meters squared, the coefficient of lift is 0.8, and the plane is flying at sea level. What is the lift force? right? So remembering the equation, it's 1/2. So this is again taken from just a known quantity that you can look up for the air density. This is the speed, right? We're squaring it like I talked about, and then the lift coefficient and the area. Now, this is what it ends up being. So this is actually 7.8 million newtons. So it's actually a really big amount, but you have to keep in mind that some of these factors are unrealistic. So this lift coefficient is actually pretty high for planes that are trying to fly at a level like sort of orientation with zero with almost no angle of attack, which is what they do when they're in cruise. Uh, this is also insane because this is sea level and this is flying really fast, so the drag forces would be insane. Like nobody would be flying at sea level while trying to go supersonic, which this is almost. Yeah, you multiply by 3.6, so it actually is supersonic. Yeah, nobody's going to do this, and this is actually a pretty significant area as well. So yeah, pretty ridiculous number. Okay, let's talk about drag. So I'm not going to go into every like factor here because basically all of them carry over. Yeah, this density, flow velocity is the same. Projected area is actually different. So instead of projecting from the top, you project like from the front, like you project the area that's punching into the air. Uh, and drag coefficient is not the same. That that that's going to change. It's going to be a different one. Some vehicles will want to optimize drag coefficients. Some will want to optimize lift. It really depends. So you can manipulate them separately. They're not dependent on each other. So yeah, like this drag can often be useful, right? Like think about planes or sorry, spacecraft that are trying to re-enter from orbit. If drag didn't exist, they'd have to use thrusters and use a lot of fuel to slow down, the same as they did to go up. But drag actually slows down. How does it do this? Well, it does it basically through heating. So as air is compressed, it gets heated, and that takes a force to do that to the air and the air. So it's again like Newton's third law, and the air pushes back onto your vehicle. Okay, so an example problem with drag. So a rocket is traveling at 8,000 kilometers an hour at an altitude of 50 kilometers. The area hitting the airstream is 4 meters squared, and the CD coefficient of drag is 0. 0.4. So it's like not the best, not the worst, right? What is the drag on the rocket? So I kind of picked this to just kind of show. Um, this is kind of a typical like altitude where first stage boosters separate, and yeah, I'll just cut to the conclusion before explaining. So you can see how this like number isn't too huge. Like for such a big area, that's not a lot of pressure. And this is why like rockets don't explode instantly when they uh, when they separate, right? Because sort of scooping shape that are of the inner stages is not very good. Not very good. It has a high coefficient of drag, and if you have insane numbers here, that will literally rip apart your aircraft or spacecraft or whatever. So just want some put some insight there. Um, so yeah, let's work through the problem, right? So let's yeah, 1/2 times. Okay, see, this is the air density. See, even 50 kilometers, it's like 1,000 times lower than what it was at sea level. Uh, yeah, this is your speed. It's getting pretty high, right? Yeah, you can see it. Yeah, then just plug in your coefficient of drag and the area. Now, actually, let's look through the units because this is what I always do. I want to make sure I have the correct units, right? So this meter squared times this meter squared is meters to the fourth, right? This is meters cubed, so this cancels out and this just becomes meters. And you have this seconds here. So, oh, and the second gets squared from up here, so it's seconds squared. So you have kilogram meter per second squared, and the units work out. Okay, I said I was going to come back to this diagram, so let's put it all together. So, the first equation up there, is basically saying what is your net force along the direction of your flight, right? So this is mass d over dt. U is vehicle velocity. So the derivative of velocity is acceleration. So ma, we know that's force. Okay, so this first part, F cos psi minus theta. So psi is, you can see from here, the direction of your thrust over the horizontal reference, and theta is the direction of flight over the horizontal reference. So you can see that you take the angle between your flight and your thrust and flight, and here's this line points to this vector over here. So you can take a cosine if you know what that is. If you don't worry about it. You'll learn in grade 11, I think. Yeah. So minus drag. You see, you don't have to do any fancy trick to drag because drag is always directly opposing motion. And this mg sine theta basically takes into account the gravity component that's opposing your flight. It's down here in this chart. Okay, so this is basically the vehicle acceleration perpendicular to the direction of motion. Now, I don't honestly understand this notation myself, but why it's like this, why it's the derivative of angle with respect to time. But I do know what it means. It's basically saying like I said, what acceleration is perpendicular to direction you're flying. So perpendicular to this reference line here, this u line, this direction of flight line. This one, right? So f sine psi minus theta, so that's taking into your vertical thrust component, plus lift. So like we said, lift always is directly perpendicular to the direction of flight, minus mg cos theta. So mg cos theta is the gravity component that's accelerating you perpendicular to your direction of flight. And then you can do, this diagram here, down here, demonstrates sort of what happens. So you do some vector addition. So you break up all the vectors into their components and add them together to see what the net force on your vehicle is. Again, if you're like in grade 9 or something, don't worry. Like you'll be fine. You'll learn this later. And yeah, so what you can do is divide every single term by mass to figure out acceleration. And that's all this is saying, and maybe plug in the equations. So yes, for example, so this one here is analogous to this one, this parallel to direction of motion, right? And yeah, all they did is just plugged in the drag formula. Yeah, and you can see some stuff cancels out, like this m here cancels out because it gets divided out. And yeah, same thing for this one here. Yeah. All right, let's do a problem with some vector addition, right? So a vehicle is flying through the atmosphere. The drag is 4,000 newtons. The lift is 5,000 newtons, and the thrust is 2,000 newtons, and the weight is 5,000 newtons. So assume it is flying perfectly level. I'm not going to do any of those crazy one with angles because it would literally probably take 3 slides to solve. I'm not kidding. So I'm just going to do a simple one. So assume it is flying perfectly level. What is the net acceleration? So in order to get acceleration, first we need to figure out what the net force is. So let's look at our horizontal forces. So when you're flying horizontally, drag is horizontal, and if you're thrusting horizontally, which we are in this case, thrust is also horizontal. So we had a thrust of 2,000, and our drag is actually pretty big, 4,000. So you can see that our net force is going to be like negative, so we interpret that as 2,000 newtons backwards. Let's look at our vertical forces. So lift and gravity, right? Gravity is always going to be directly vertical, and if you're flying perpendicular to the ground, then your lift will also be directly vertical. And for this case, I made them the same, so weight is 5,000 newtons, and lift is also 5,000 newtons, and you can see there's a force balance, and you're not accelerating up or down. Now, let's do the last component of the question. What is the net acceleration? So if you look at the Newton's second law formula, so force is mass times acceleration. To get acceleration, all you do is just take your force and divide by your mass. Now, this is our force, right? Our horizontal component is the only one we need to consider, right? So just plug the 2000 in for going backwards. Now this is interesting. This is um, looking at the gravity component, right? And to take force, you just need to divide by the acceleration of gravity to get the mass, right? So this is all this does. So 5,000 kilogram meters per second divided by 5,000 kilogram meters per second squared divided by meters per second squared, right? Gets us kilograms to plug into this. Uh, yeah, and this crunches out to 3.92 meters per second. Now it should say backwards because acceleration is a vector quantity, so you need to specify what your direction is as well. That was a mistake on my end. Okay, let's talk about some quantities. So some velocity quantities related to rocket exhaust or rocket nozzles, just so that everybody's clear on what they all mean. So V2 versus C star. Now these can have other names, but I think these are the most common ones. So V2 is what you get if you basically just pointed like a radar gun, right, at a particle leaving your exhaust and measure the speed that it's going at. Uh, it's about as simple as that. I mean, there's nothing else to say really. Um, C or effective exhaust velocity. Okay, so the purpose of this, basically, from what I've seen, rocket engineers like to have a lot of different variables so that they can make their equations simpler, even if you have to keep track of a whole lot of variables and it can be confusing. So all effective exhaust velocity does is compensate for the pressure thrust a rocket engine can create. So you can just plug it in and pretend like all of your energy is being converted into, sorry, all of your thrust is momentum thrust and pretend like that's it and plugging it into the force thrust equation, so mass flow rate times that effective exhaust velocity here, right? Um, so to crunch that, all you essentially do is take your initial actual exhaust velocity, your real exhaust velocity, which is V2, and you look at this pressure thrust section here, divided by mass flow rate to get another speed that you add to this. So that you can just plug in this directly and don't have to worry about that pressure thrust section when calculating it. I mean, and it also, I guess, has another use where it's like a measure of the efficiency of your uh, rocket in general, like and similar to ISP, if you remember from last week. Um, yeah, that's pretty much it. So characteristic velocity is another one rocket engineers sometimes use, and it's really not a velocity at all. It's kind of just an efficiency of how well a rocket engine creates pressure with a certain amount of mass flow rate. Now, yeah, so like it says here, is basically a measure of the combustion performance. In other words, how good, yeah, so I said that. Now, often what engineers will do is compare the C star to this C, and the C will always be higher. If it's not higher, you're doing something wrong. And you could create something called the coefficient of thrust. And what that basically tells to you is how good a rocket nozzle is performing. Let's do an example problem. I think this is my most complicated example problem. So, yeah. A rocket engineer measures the speed of a rocket's exhaust to be 2020 meters per second. He is at sea level and he knows the rocket consumes 100 kilograms of fuel in 50 seconds. If the area of the nozzle opening is 1 meter squared, and this engineer wants to achieve an effective exhaust velocity of 2,500 meters per second, what should be the pressure at the opening? All right, so you take this formula for effective exhaust velocity, sub in all your known values. It's pretty straightforward, right? Okay, then you just solve mathematically or algebraically, right? So let's actually take a look at the units before doing that to make sure we haven't messed up. So when you're solving this, you multiply this, which is just going to be 2 kilograms per second, um, to this side. Oh yeah, first you need to subtract this from this to essentially get the difference in velocity based on thrust, kind of, in a way, right? So what you do is, yeah, multiply this into here. So what you get is kilograms times meters over seconds times seconds, so kilogram meters per second squared newtons, right? Then you have just this part over here left, so pascals times meter squared. A pascal is a newton over meter squared times meter squared, just a newton, right? So we know that our units are consistent across the two sides, and we're happy. All right, so yeah, just crunching the numbers, right? Uh, this is going to be like newtons times newtons at this point. If you divide both sides by this area, um, what you're going to have left is, this is a mistake, by the way. Oh no, it's not. It's fine. I just didn't incorporate this. Sorry. No, don't worry about it. Don't just ignore what I said. This is all still good. Um, yeah, you just crunch the number and you get your pressure at the opening. So you can see that the pressure is almost identical to atmospheric pressure. So essentially what this probably means is that made the stats of my rocket too overpowered, so that increasing the nozzle, I made it too big. So increasing the pressure of the nozzle a little bit will have a big effect on the exhaust velocity, effective exhaust velocity. All right, so let's review. I think Biscuit or Christian mentioned this briefly last week. So let's review the mass quantity. So engineers have a lot of these different like mass quantities that they'll use to measure rockets, and there's a lot of different ways to break it down. I mean, a lot of these are, I mean, really all of them are very self-explanatory. Like they don't need to be explained too much, but just keep in mind, I guess the most important two to know is propellant mass fraction and mass ratio. So uh, propellant mass fraction is propellant mass, so this section over the whole vehicle, like fully fueled and everything in it, and it's like complementary to mass ratio, which is the empty vehicle over the initial mass. And you can see that represented in this sort of equation down here. Uh, yeah, that's all there is to it, really. It's not too complicated of a unit of units. Just have to be aware of what they are, and there's a lot of them to keep track of. Like there's also like mass payload that will be encountered maybe later on in some more complex or just different like formulas, maybe to like calculate your payload to orbit capacity or something. Okay, let's talk about the fundamental rocket equation or the ideal rocket equation. Has many names. It's all about the same thing. So what it's a measure of is it's how much can the vehicle change its velocity. It's actually a pretty simple idea. Now for rockets, since they go to space and often there's very little forces slowing them down, they have unlimited range. So really measuring range is kind of useless in rockets. Their capacity or capability more is better represented by measuring how much they can change their velocities by. Um, it's kind of a measure of energy relative to size as well. Like have to mention how looking through this, right? There's no thrust and there's no mass. So really those don't have an effect on how much you can change your velocity by. It's sort of all your efficiencies. So uh, yeah, so and it's always assuming to be in a vacuum and ideal conditions. Like because if you're saying the atmosphere, you won't be able to change your velocity as much because there will be like drag and gravity and other forces slowing it down. But let's look through this. So it's effective exhaust velocity. So remember we talked it's here it's VE. I think I had it as C, right? So that's basically an efficiency of how well your rocket engine is accelerating particles that go through it. So that's your kind of engine efficiency. Now this right here is sort of the inverse of the mass ratio, the MR. So this is your fully fueled mass with the rocket and your empty mass. It's also called dry mass. So the closer this gets to one, sorry, no, it's the other way. The bigger this is, the better, right? Yeah. Um, Now This is kind of an efficient, a measure of how efficient, I guess, you're using your weight, how much of it is actually fuel. Now, the way you calculate this is you take the effective exhaust velocity and you multiply by the log, the natural log of this value here. Now, if you think about it, if all of your rocket is fuel, right? This MF is going to approach zero, and this is going to like stay the same, right? So it's going to approach large numbers. So yeah, what's going to end up happening is it's slowly going to trail off and approach infinity as a logarithmic function. You'll see that in the next slide. Um, and yeah, VE can be expressed as ISP times gravity. Now, this kind of goes to show from last week, like ISP is just another way of measuring effective exhaust velocity, and you can see that this gravity has no effect on the ISP. It's just a constant scalar. This G naught means on the Earth's surface. It's always just going to be a constant like scaling factor on this ISP. All right, so yeah, this is what I said I was going to show. So this is some extra insight for this rocket equation. Um, so you can see that this VE component is linear from this part of the chart, and the mass ratio is logarithmic, or yeah, logarithmic. So you can see how it kind of trails off as you get better and better ratios, while this is just like linearly increasing. And it kind of makes sense. Like if you think about it, your rocket engines are going to be the most powerful relative to your mass. Your like thrust to weight ratio is going to be the highest as your propellant tanks are depleted, as they're like almost empty. So this is why most of your gains are in the beginning when your vehicle is the lightest, by improving your mass ratio, one over mass ratio, I should say. It's the reason it could be like just mass ratio, but then you'd have to have a negative out front because the log would be like flipped, right? So this is there's many versions of this equation that are around there. So yeah, like it just shows, I guess it's there's a lot of like data on here. You can see like as you increase your ISP, this gets scaled, and you can see kind of the relationship of your mass ratio. And same thing on this side. So for a propellant mass fraction, again, I don't know why they're using two different like ways of measuring mass, but again, it's like similar in many ways. So you want your propellant mass fraction to be the highest and mass ratio to be as low as possible, just as a review. So you can see if you're pretty much 99% fuel, it's like very close to very well optimized, right? Compared to all these smaller values. And you can see like initially like your slope changes by law and it just progressively changes less and less. Also noted by this like logarithmic property here. Uh, so yeah, not much else to say. Let's do an example problem. So a guy made a well-performing rocket engine. It has a specific impulse of 400 seconds. He wonders what percentage of uh, okay, this is wrong. So what percentage of fuel should it have in order to be able to go to Mars? I should have deleted this part. I should have asked the what the ISP is. What the sorry delta V is. When the mass when it is empty of fuel is 400 kilograms and a full tank weighs 3,000 kilograms. With a full tank, it weighs 3,000 kilograms. What is the maximum possible change in velocity of this vehicle it can accomplish? All right. So ignore this part. This I just should have deleted it. So see that first part in the equation, your exhaust velocity. So just plug in your values and crunch it out. Yeah, the seconds cancel. Seconds, meters per second, right? All good. And this ln, full mass versus dry mass, is just a scaling factor. Like these kilograms will cancel out, and you just get like sort of coefficient that you just multiply onto here. Uh, and yeah, this is what it crunches out to be. This is actually orbital velocity, so it's actually a pretty good rocket. Like the ISP is high, the mass ratio is good. Sometimes it's higher, but it's actually pretty good. But even with these awesome stats, you can kind of think, oh, while you're trying to go to space, gravity and drag would slow you down. So you think, how is it even possible to make a rocket that can go to space then? Well, the answer is staging. This one, it's going to carry all that fuel tank mass the whole way through, and it's going to have to do everything in one step. And when you do staging, you just need to do a bunch of smaller delta V's changes, and it's basically more efficient to do it that way in general. All right, so let's talk about the last topic for today, efficiencies and power. So they kind of go in a step, right? So I'll just go to this diagram first. So the first little bit of loss is combustion. It's combustion loss. So uh, that is essentially saying what part of your fuel actually like reacts and the bonds get broken and it reacts like the way you want it, right? And that's usually very well. It's maybe like 99% efficient. Then you have heat loss through the walls of your engine. So the particles that are on the outside will give some of their heat to the walls, and then the walls have to be cooled with the technology, which we will probably talk about in a future presentation. Then you have this, like, you know how exhaust, when it leaves, it's glowing hot, right? So it has a lot of heat still within it that it can't always be completely turned into velocity. So that cuts off a big chunk. And then residual kinetic energy is essentially when your particles leave your rocket engine, they're still moving. Sometimes they're moving out fast, really bad. And what would be optimal is for them to be still in space. So all the kinetic energy goes to you rather than having some of it go to you in your vehicle, but a lot of it going to your particles that are leaving your exhaust, your gases that are still moving super fast and have that wasted energy within them. So let's talk about the formula. So internal efficiency. So I won't talk about combustion efficiency because the formula for that is super complicated and like just chemistry. But internal efficiency is basically saying how well does it turn the stored chemical power, and it takes it into the combustion efficiency into consideration as well here. Uh, how well does it take the stored chemical power and turn it into the kinetic energy in your jet? So what it does, it takes into this formula takes into account this loss and all these losses, but not this loss. This loss is this formula, which I'll get to, right? So it's the power in your kinetic power in your jet times the combustion efficiency times the chemical power. Now, just to be clear, power is basically like how quickly you can apply a certain force over a certain distance. Now, mass times velocity is thrust. So just have force times one of these velocities, right? The exponent will go, and you'll have force over speed, and force speed is distance over time. So force times distance is energy over time. So that's just another way of thinking about power. It's like how quickly energy is deployed. Anyways, don't worry about it too much. These are all the ways of calculating the power in your jet. And yeah, just plug into here. And propulsive efficiency is saying what part of those like of your kinetic energy that you're left with is actually going towards the rocket and not towards like those exhaust gases which you don't care about. So here it is. The derivation is actually a little bit like complex. You have to do some math. It's well, the idea is simple, right? Like vehicle power plus residual kinetic jet power over vehicle power. But to get from this step to this step, you have to do some like crazy math manipulation. Believe me, I went through it. It's actually kind of interesting, but it's a bit tricky. And this is also another graph that could give insight. So essentially, it's saying like your velocity ratio, so how your vehicle speed compared to your exhaust gases speed, and you can see that when it's optimized when they're the same, right? Because your vehicle will be going some speed, say it's going like 1,000 meters per second, but your exhaust gases are going to get ejected at 1,000 meters per second, so they're actually going to be still in space. Okay, example problem. This is the last example problem. So a vehicle's combustion efficiency is 90%. The chemical power flowing through it is 1 megawatt. It has 1,000 Newton thruster and it's 1,000 meters per second velocity at nozzle opening. What is the internal efficiency? Okay, let's do that first part right now. Okay, so yeah, plugging. This is the. If we go back to the previous slide, There's many ways of expressing power jet. I'm going to use this one, 1 half V2 squared. Or yeah, 1 half F V2. No squareds. So yeah, plugging in F, plugging in V, 1 half, boom. Um, Combustion efficiency, turn that into decimal here, 1 million watts. Okay. Uh, yeah, this is power because this is just a scalar times power. This is power because it's force times speed. We know that's power. So yeah, if you crunch this, it's 0.51. So it's actually like pretty average for what typically you see. Not too bad, not too bad. Um, okay, so assume it is in space and traveling at 5,000 meters per second. What is the propulsive efficiency? Okay, we can reuse this. This is just C. So U is 5,000, U over C. Yeah, plugging it in. I mean, not much to say, right? Uh, yep. So yeah, if you plug it in and crunch the numbers, you get this number here. So uh, and that's just over this as well. So you multiply these two together to get your total efficiency. So it's going to be pretty bad. Like it's not the best. Maybe going to be like 0.220. I think most like rockets try to aim for, I don't know, 30 to 40%, but it's actually pretty hard. Like if its efficiency is very hard to optimize. So yeah, I mean that's the end of the presentation. I'm happy to see all of you here. It was fun. Thanks for coming. So next lesson is going to be probably the best part of a month away, and it's most likely going to be a lesson on satellites from Lauren. So great to see all of you here.
Yay!
Any
Thanks,
questions?
Vlad.
Any questions? I forgot to ask in the middle for questions again. I'm so sorry. I was like after last time I thought I should have done it, but I forgot again. So my bad. Uh, Varun. Let's see. I don't even know when we come back. Maybe the first week, probably the second week after we come back. There's some talk of the Christmas break getting extended, so it might be a while. Sure, Ethan. Let's have a look at it. So which part of it are you concerned about? Oh, okay. Okay, awesome. Maybe I could have mentioned the dimensional analysis on this part as well. So like it's actually very easy. There's these meters per second cancel out with these meters per second, these meters per second cancel out with these meters per second, boom. You just have numbers. I think that's partly why there's this like crazy what's it called? Like this is actually just this is derived from this. So you just need to do some crazy math and manipulation like to convert from here to here. But this is super simple because you only have two variables and they instantly like the dimensions like cancel each other out and all you're left with is numbers. So it's actually a pretty neat little equation. And it gives you this curve if you sub 2 over UC as a one variable. Yeah, I'm gonna stay here for a bit. If anybody thinks of any questions, I'll be glad to hear them. Oh, I haven't finished. I'm gonna do that over the break. The sub apps. McMaster, Toronto, and UW. One for each. Oh, Human. It varies. So often they'll use like titanium, and then run like ducts through it, or actually cooling is more important than your thruster material. So it can be anything really. But yeah, typically like something that's conductive, like often copper is used because it conducts the coolness from the fuel that they pump through it, which is kind of counterintuitive, right? Because you'd think that they'd want to be like insulated from the heat of the combustion chamber, but actually the fluids that you pump through the walls of it are very cold, and you want and if it's not conductive enough, you might get like the inside of your combustion chamber melting while the rest of it remains cool. So often it's like very conductive metals like that, and strong metals like titanium and copper, and many are used. Depends on the area as well. Uh, yeah,
Okay, thank you.
no worries. It's a pleasure answering your question.